r equals 0, r equals 1, and ck plus 1 equals k plus r minus 1 times ck divided by k plus r plus 1 times k plus r for k greater than or equal to 0. Now we work on each r, 1 r at a time. For r equals 0, the recurrent relation gonna be ck plus 1 equals k minus 1 times ck divided by k plus 1 times k. Okay? And as we use this for k greater than or equal to 0, if k equals 0, we get C1 equals negative C0 over 1 times 0. That's the problem. So it's undefined. That means the r equals 0 doesn't work. So down to one solution at r equals 1. Then the recurrence relation will be ck plus 1 equals, now as r equals 1, the numerator gonna be k times ck divided by k plus 2 multiplied by k plus 1 for k greater than or equal to 0. Okay? And then repeat the same pattern by each ck for at least 3 of them, 3 non-zero terms. For r equals 1, ck plus 1 equals k times ck divided by k plus 2 times k plus 1 for k greater than or equal to 0, starting at k equals 0. If k equals 0, we get C1 equals 0. How nice. Would that work out? We'll see. And then the other one, let me see, we have for k equals 1, we have C1 equals, no, C2. C2 equals 2 times C1 divided by the C is 0 times C0, which is 0. So C2 is 2 times C1 divided by 3 times 2, which is 1 over 3 times C1. Since C1 is already 0, we get C2 equals 0. And the same as the rest of them because we used the previous C to find the current C. So Cn gonna be 0 for n equals 1, 2, 3, and so forth. But our hope to get non-trivial solution is for C0 not equal to 0. Otherwise, we have no solution. Okay. So we're going to put the notes here. So assume C0 is not 0. Then the solution, the y in the form of the summation Cn x to the power m plus r, and r is 1, which is summation Cn x to the n plus 1, n from 0 to infinity, or in the expanded form as x to the first multiplied by C0 plus C1x plus C2x squared, and so forth. And this solution gonna be just x to the first power and C0 assume not equal to 0. And then the rest of them is 0. Now we get just one solution, y equals x. Okay. So the only solution that come out as we use the Frobenius method. And now we're gonna find the second solution using the second solution formula. So as y1 equals x, we're gonna find y2 using the formula y2 equals the y1 integral e to the negative integral px dx divided by y1 squared with respect to x, and back to the standard form of the differential equation that we have, which is y double prime minus 1 times y prime plus 1 over x times y equals 0. That means the px equals negative 1, and the qx, which is 1 over x, we do not use the qx in the formula, we use the px. Okay, so put in the formula here as y1 equals x integral e to the negative integral negative 1 with respect to x divided by y1, or the x power 2 with respect to x, and the exponential, we're going to be e to the first power, integral of the 1 going to be x. So the top is e to the x, the bottom is x squared with respect to x. And with this, how to find the solution? Well, if you rewrite it as the form of x to the negative second times e to the x, you might think about the by parts, but this time by parts or the tabular by parts doesn't work because the power here x to the negative second is kind of repeating form of the integration. So what we have to do here is to use the Taylor series point. We cannot find the solution using the analytic way. So we have to use another way. Let me write it as, so y2 equals now x integral 1 over x squared multiplied by e to the power x with respect to x. And this time we're gonna use the Taylor series expansion of e to the power x as 1 plus x squared over 2 plus x to the third over 3 factorial, so this is factorial, plus and so forth as a Taylor expansion of e to the power x, and then do the antiderivative term by term. So the first term here is 1 over x squared plus 1 over x plus 1 over 2 factorial plus x over 3 factorial plus maybe keep going like x squared over 4 factorial and so forth with respect to x. And then from doing the antiderivative term by term, 1 over x squared is x to the negative second. So we have negative 1 over x as an antiderivative. 1 over x we give the natural log x, and then the rest of them just the power rule of the antiderivative. Okay, and then we multiply all by x to get negative 1 plus x natural log x plus 1 over 2 factorial x squared plus x to the third over 3 factorial times 2 plus x to the fourth over 4 factorial times 3 and so forth. As you see, the second solution has the natural log x involved. It's from the use of the formula to find the second solution. So the Frobenius method will give at least one power series solution. If you have only one, another way to find the second solution is use the formula to find y2.